And start screen sharing. Everybody seeing this? Right.
Yes.
Okay, so all right. Today I want to cover essentially tensors. And we're going to be using as our kind of prototypical example of a tensor, something we've already learned about just now, which is the metric tensor, which comes from that bilinear form that acts on v cross v to v to r. And once we define what a tensor is, we'll do a little bit of algebra with them. So I mean algebra in this sense, the same kind of algebra that you've been seeing since high school already. And then I want to show you that, even though tensors have this very fearsome reputation, you've already encountered them in many ways before. In particular, in two ways that you will have encountered them. We'll probably cover one today and one on Monday, but two ways you've already seen them before. And this is the idea of linear maps and bilinear forms. So both of these things have already, you've worked with, possibly not in calling them like this, but you've worked with them, you're familiar with them. They actually encode information as tensors. Okay, so let's get started then. As I said, when I was growing up, as an example, tensors had this rather fearsome reputation, just some sort of mystical object that you only really understood after being exposed to general relativity. So, we did linear algebra, we studied a whole bunch of things in linear algebra. And then in some sense, you were exposed to the idea of a tensor and tensor calculus if you did general relativity. But general relativity comes with a whole bunch of other baggage that you have to kind of wade through first. And in doing so, these ideas kind of got merged into each other, and it wasn't clear what it is tensors were outside of general relativity. So what I want to show you today is that actually, in truth, we've already done most of the heavy lifting when we learned about vectors in the last two lectures. And this comes from the fact that we took the idea of a vector as a geometrical object, as something that having magnitude and direction, and we changed that definition into a more algebraic definition where a vector was, loosely speaking, something that transformed in a particular way under coordinate transformations. And I said that the reason we wanted to do this is not particularly because we wanted to be able to manipulate vectors easily, although that's one of the nice things about that definition. It was because we wanted to generalize vectors. And this definition of something that transforms in a particular way, transforms as a vector, transforms as a spinor, transforms as a scalar, transforms as a tensor, is precisely that definition that allows us to generalize from vectors to tensors, right? So in fact, I'm going to introduce tensors in two ways. I'm going to introduce them first as sets of numbers that are labeled by some indices that transform in a particular way under change of basis. And this is something that we're already familiar from vectors with. And the second way is going to be as elements of a vector space, It's really going to be what we would eventually call a tensor space. But it's a space that kind of behaves like a vector space. It's constructed from multiple tensor products of the vector spaces V and the dual vector space V star. The second definition, the definition that's built on taking tensor products of vector spaces, is really a basis independent statement and only relies on the understanding of linear maps. Okay, so it's actually a very powerful way of thinking about vectors as well as tensors, as well as some of the more exotic objects that we may encounter at a later stage. So again, we're going to give two definitions of what a tensor is. And these two definitions are the first is going to be a basis dependent statement, and the second one is going to be a basis independent statement. And they're entirely compatible with each other, and I encourage you to think about them in an interchangeable way. So let's start with the first definition. And the first definition comes from thinking about vectors in using a particular basis. And in particular, thinking of them as, tensors as sets of numbers that are indexed in a particular way and that transform in a particular way under a change of basis. So suppose I have some basis, let's say E mu for a vector space. So suppose that E mu and E mu prime are bases for the vector space V, right? Then we know that we can express E in terms of E prime or E prime in terms of E. So under a change of basis, that we've been hopping on for the last 2 lectures, where E mu goes to E mu prime, and E mu prime was related to E mu by A inverse mu nu E nu. The metric tensor that I introduced the last time as the components of the bilinear form is given by G prime equal to G of E mu prime E nu prime. In other words, I have this bilinear form, and when it acts on the basis vectors mu and nu, then it produces components G mu and nu. And when I made the change of basis from E mu to E mu prime, G acts on E mu prime, E nu prime to give me G mu nu prime. Okay. In terms of the old basis, E mu, the following is true. G mu nu, which is G of E mu, E nu, is G of A mu lambda, say, E lambda prime, A nu, let's say sigma, E sigma prime. Again, lambda and sigma are just indices again. Right, and this is the expression of the old basis in terms of the new basis. Okay. Because this is a bilinear map, it acts only on the vectors. So it acts only on the basis vectors, which means that I can pull these components out. So this is A mu lambda, A nu sigma, G acting on E lambda prime, E sigma prime. But this guy here is what we just agreed gave the components of the metric tensor in the new basis. Or the metric gave the components of the metric in the new basis. So this is A mu lambda, A nu sigma, G prime lambda sigma. In other words, both of the indices of G mu nu transform like the downstairs indices of a covector. And we say that G mu nu transforms as a doubly covariant vector. So since both indices transform like covector indices, we'll say that G mu nu transforms as a doubly covariant tensor. Yeah, that's just a definition. As an exercise, I will leave it to you to write out the components of G mu nu explicitly in terms of the components of G mu nu prime. And to make your life easy, let's just say for a two-dimensional space where the indices mu and nu run 1, 2. So write out the components of G mu nu, by which I mean G11, G12, etc. explicitly in 2 dimensions. So far, I've shown you that the components of the metric that we defined by its action on the basis vectors on a vector space transform in this particular way, which I said makes it a tensor, makes it a doubly covariant tensor, meaning that both of its indices transform like the covariant indices of a covector. Right? But I can generalize this because, well, 1, 2, 3, who cares how many indices we have, right? Their properties are defined by the way they transform. So more generally, if I have some set of numbers, let's say Q with P indices upstairs and Q indices downstairs, so with indices that run from 1 to the dimension of the space that we're working in, the vector space we're working in. And this thing transforms in the following way under the change of basis that we usually talk about. So Q alpha 1 through alpha P, beta 1 through beta Q is A inverse alpha 1 alpha 1 prime through A inverse alpha p prime A beta 1 prime beta 1 through A beta q prime beta q times q alpha 1 prime through alpha p prime beta 1 prime through beta q prime. This times here is just the fact that I can't fit this on one line, so it's normal multiplication. Okay. So if I have the set of objects Q that transform in this particular way, then I will call this Q the components of a tensor of type P Q. In other words, I've got P upstairs indices, Q downstairs indices. Okay. So then Q alpha 1 through alpha P, beta 1 through beta P Q is the components of a tensor of type P Q. This corresponds to the number of superscript indices and the number of subscript indices on the tensor components. And in particular, the sum of those two numbers, P and Q, is called the rank of the tensor. Okay. So as an example, metric tensor, G mu nu, is a rank 2 tensor of type 0, 2. Is everybody happy about this? Okay, great. So there are a few points that we should keep in mind. The first of these is that only tensors of the same type may be added to each other. So I can't add a tensor of type 2, 0 to a tensor of type 0, 2. That doesn't make any sense, right? In order for me to be able to add or subtract tensors together, they need to be of the same type. Second point is that upstairs indices can only be summed with matching downstairs indices. I can't sum an upstairs index with an upstairs index. If I have a mu and they're both upstairs, then I don't sum over that. There's something wrong. Okay, so only upstairs and matching downstairs indices can be summed in the Einstein convention. The third point is quite important if you're working with these things, especially if you're doing horrible index calculations in GR, is that if you find that any expression that you have has more than 2 repeated indices, you've done something wrong somewhere. So you cannot have more than 2 repeated indices. And then finally, if any of these conditions are violated, we don't have a valid tensor equation on our hand. So you can certainly write down an expression, but that does not mean that that expression makes any sense. And when I say you don't have a valid tensor expression on your hands, what it means is that that expression will look different in different coordinate systems. If any of 1, 2, 3 are violated, we will not have a valid tensor expression. As an example of this, suppose I have the expression A mu nu lambda equal to B nu mu lambda plus C mu nu lambda sigma sigma plus D mu nu lambda tau. This expression is an invalid tensor expression, okay? Because each of the terms in this expression on the right-hand side are just wrong in some way. And I'm going to leave for you as an exercise to tell me why. Why is this expression invalid as a tensor expression? Right. So let's list down some properties of tensors that will be useful in defining operations for us, that will be used quite a lot in what follows. Okay, so the first one is that the sum of 2 or more tensors of a particular type produces another tensor of the same type. So if I give you one type 02 tensor and another type 02 tensor, and you add those 2 up, you're going to get another type 02 tensor. So the sum or difference of two tensors of the same type results in another tensor of the same type. Point two is that I can combine tensors by multiplication. What I mean by this is that I can increase the rank of a tensor by multiplying two lower rank tensors. So, for example, if I have a tensor lambda, lambda, say mu lambda, and this is a type 1, 2 tensor, and B, say alpha, beta, gamma, delta, and this is a type 2, 2 tensor. Then the tensor C, mu, alpha, beta, nu, lambda, gamma, delta, that I form by multiplying these two together is clearly a tensor of type 3, 4. So that's how we increase the rank of a tensor, right? And then finally, I can reduce the rank of a tensor by an operation known as contraction. And what contraction is setting pairs of indices, and it's important that the pairs be one up, one down, equal to each other, and then summing. So we can reduce the rank of a tensor by contraction of indices. Let me do an example to illustrate. Suppose I have a 2, 4 indexed, a 2, 4 tensor, C, alpha, beta, gamma, delta, mu, nu. Then the tensor that I get by taking C and writing it as alpha beta. So because the alphas and the betas are upstairs and downstairs and they match, they're summed over. So that's alpha summed over alpha and summed over beta. So the only free index in this is mu nu, right? So I started off with with C alpha beta gamma delta. I've set the gamma delta equal to alpha beta, and if I find that they match upstairs and downstairs, then I have to sum over them. So then I apply the Einstein summation convention. So the alpha and beta then become dummy indices in that sum. So what's left as free indices are the mu and the nu. So there's a mu and the nu on the left-hand side and a mu and the nu on the right-hand side. So even though this looks like a type 2-4 tensor, because these indices are the same and summed over, in other words, they're contracted, it is really just a 0-2 index object. Okay. What I'm going to leave for you guys as an exercise is to explain why contraction actually produces a tensor. So all I've said is that I've taken an object of type 2-4 and I've produced an object of type 0-2 out of it. And that's just counting indices upstairs and downstairs. But in order to demonstrate why this thing should be taken seriously as a tensor, you have to show me that it transforms as a tensor given the transformation properties of the C. So explain just excuse me 1 second, please. So explain why contraction produces tensor. Okay. Any questions so far? All right. So tensors and their properties, as we've defined them through the transformation properties of these objects, may seem new and a bit abstract, maybe. All right. We're just literally just talking about making coordinate transformations. I haven't actually made a particular coordinate transformation yet. I've talked about coordinate transformations in a general sense. And all of these things that we've learned about tensors and actually vectors as well and covectors are all fairly general things. So they might seem a bit new and a bit abstract, but, and you may not realize this, you've already met such objects in the past, in particular in linear algebra, in your study of linear maps and what are called quadratic forms. So let's start with linear maps, and I think that will take us to the end of this lecture. And then next time I will talk to you about quadratic forms, which derive from bilinear maps, and show you that both of these things are actually tensors. They transform like tensors, but you might have seen them transforming in a different way. That different way is nothing but encoding the tensor transformations already. So something that you've seen already in a linear map. So a linear map with regards to vector spaces is a map from a vector space V to itself. So a linear map, let's say M, that takes V to V, exists independent of any basis. So I don't have to pick a basis on the vector space or anything. I can just tell you how to map elements of the vector space to other elements of the vector space. They don't need a basis in order to work. So it exists, let's say, independently of any basis on V. Okay. And what usually happens is that we don't work with the map itself. We work with a representation for the map. So we can find given a basis, we can find a representation of that map in that basis. And the way we do that is by taking the action of that map on the basis elements. So given a basis for V, we can find a representation of M as M acting on the basis vectors. Remember, M takes in vectors and produces vectors. So M acts on the basis vectors E mu to produce some linear combination. Let's call it nu mu E nu. So again, it takes vectors to vectors. So it acts on the basis vectors E mu to produce another set of basis vectors E nu, or some linear combination of the basis vectors E. And these numbers here, the M nu mu, are precisely a matrix that represents M in that basis. So this is a matrix representation of M in the basis E mu. Okay. This is, of course, a basis-dependent statement. So a different basis will produce a different representation. The matrix that will represent M will look completely different. Okay. So the question we should ask ourselves, if I'm telling you that this thing M mu nu is a representation that is actually a tensor, is how does this thing transform? Okay. So towards that end, suppose that, well, firstly, let's try and understand what happens when I act on vectors. So I told you what happens when I act on basis elements. So what happens when I act on vectors for them? So suppose the vector y I get by taking the vector x in V and acting on it with this map M. I'd like to understand how the components of y and the components of x are related. Okay, it's going to be important in a little bit. Essentially, because y is mx and y is y mu e mu. In fact, let's write it y nu E nu, and M acting on X is the same as M acting on X mu E mu. So if I just expand X in the E mu basis, M acts on vectors. M acts on vectors so I can pull the x mu outside. That's just x mu, M acting on E mu. And we just decided that M acting on E mu produces M nu mu E nu. So that's x mu, M nu mu E nu. By comparing the two expressions, this one and this one, it follows that the components of the vectors transform under the mapping M as y nu equal to M nu mu x mu. So let's keep this in mind. I'm going to need it, so I'm going to call it equation 2. So if you look at this, equation 2 is just the component form of the following matrix equation. It says that y is m x, where here we're talking about matrix multiplication. In other words, the matrix representation, that's matrix multiplication, okay? So now let's make the usual change of basis from E to E prime. Right? So E nu M nu mu is M acting on E mu. But this thing is just M acting on A mu lambda E lambda prime under the change of bases. And I can take the A mu's outside of this expression because M just acts on vectors. So this is equal to A mu lambda M acting on E lambda prime. But M acting on E lambda prime is just E, let's call it sigma prime, M prime sigma lambda. Okay. But I need to compare the E basis to the E basis, not the E prime basis. But I know how the E prime basis relates to the E basis because this is just A mu lambda A inverse sigma nu M prime sigma lambda. In other words, the matrix representation of the linear map transforms like a 1-1 tensor. Again, all we're talking about here are linear maps, maps from V to itself, right? And what we've shown is that the matrix representation, am I missing an E on the, yes, I probably am. Yeah, let's check that out. And this is E new. Okay. My statement still holds. So my point here is that under the change of basis, under the coordinate transformation that we've been taking to define vectors and covectors and tensors, the matrix representation of a linear map on the vector space transforms like a 1-1 tensor. Okay, so you've already seen this before. Let me relate it to the way you might have seen it in the past and show you that anything that transforms in that way is really this kind of tensor. So alternatively, Let's derive a matrix form of this equation, the transformation equation. And we do that by noting that under a change of basis, the vectors x and y in the vector space V become the following. So under a change of basis, x and y in V become x prime, say, and x prime is ax, where A is the matrix of coordinate transformations, and same with y. It goes to y prime, and y prime is just ay, like such. Okay, here, I mean, you take the A mu news, you arrange them in a matrix, and you multiply it with the vector x in the usual matrix multiplication form. So if, in addition, y is equal to mx, in other words, x and y are related to this through this linear map, then the following is true. Then I know that y prime is ay, but y is mx, so this is amx. But from here, x is A inverse times x prime. So that's A inverse x prime. And this is what we would call, by definition, m prime x prime. In other words, under the coordinate transformation A, m, the linear map, goes to m prime, and m prime is A inverse. So under coordinate transformation, this is how the matrix representing the linear transformation transforms. Okay. And this is basically the statement that it transforms like a 1-1 tensor, but written out in a form that you might be more familiar with. All right, so I want to stop here for now, and then on Monday, either online or in person, I will continue by talking about quadratic forms and how we think about vectors, how we think about tensors in a basis independent way by taking tensor products of vector spaces and covector spaces. Any questions?
Sorry, yes, I just wanted to ask, we've used the term a form, like in quadratic form or a bilinear form. Is there a distinction between a form or just like a mapping or a linear mapping?
Okay, so in this case, I'm using the word form is a tricky word. I'm using the word form in the way that you would have learned it in linear algebra, which means basically mapping. So I'll use it interchangeably there. I could have said bilinear map, for example.